Today, we're happy to have Raymond Coe, who's going to tell us about gravitational wave probes of Axion rotations responsible for dark matter and Baryon asymmetry. Take it away.
All right, thank you. Thanks a lot. Yeah, I'm very excited to share with you some of the work that I've been doing regarding axion dynamics in the early universe. But before beginning the physics talk, I just want to take a moment to honor John Bartley, who won the Nobel Prize in Physics twice. The first time for the superconductor effects and their discovery of the transistor effect, and the second time for the BCS theory. He was born today, 14 years ago. Okay, so for this talk, what I would like to focus on is some early universe dynamics of the QCD axion or axion-like particle. Specifically, I'm thinking about ways that people have not realized in the past decades. Specifically, I'm looking at this potential that will go into the details. Instead of doing some oscillations of the field in the potential around the minimum of the potential, instead it is doing this kind of a spiral motion on the body of the wine bottle potential. And I want to show that this dynamics interestingly gives rise to the dark matter and the Baryon asymmetry of the universe. And the focus of this talk is how this could actually be probed with gravitational wave as a byproduct of the mechanism. So in this plot, I just want to give you a sense of what kind of parameter space I'm thinking about when I'm talking about axion-like particle or the QCD axion, especially when I discuss the production of dark matter and the Baryon asymmetry. And these are the regions that would be relevant also when we discuss gravitational wave signatures. So if we're thinking about production of dark matter and the Baryon asymmetry using the QCD axion, then for sure we have to live on the QCD band, which is showing this yellow band. And our prediction from the combination of these two matter densities is that we need to live somewhere in the heavier side of the QCD band. So of order milli-electron volts to, for example, 0.1 electron volts. However, if we're thinking about axion-like particle, then the prediction of our mechanism is that we have to live along this green band called Axiogenesis. So this is just to keep in the back of our mind what kind of parameters we're thinking about. But this plot also shows how detectable our predictions are compared to the usual QCD axion or the prediction from the conventional misalignment mechanism of dark matter. So our prediction is that the axions would interact with standard model particles at an interaction rate many orders of magnitude stronger than conventional prediction. So any experiments they're looking for axion-like particle or the QCD axion would have to pass our prediction before they get to the conventional prediction. So this is a very testable framework that we're working with. All right, so that's the parameter space that we will keep in the back of our mind. But today, I would like to discuss different parts or different impacts of axion rotation. The first is what I mentioned, dark matter. It turns out that the rotational energy density of the field that we just saw in the wine bottle potential could be the source of dark matter energy density. And as I will also discuss in detail, this rotation corresponds to a specific conserved charge that will eventually become the Baryon asymmetry, meaning more baryons than anti-baryons in the universe. The main focus of this talk is actually how we can use the so-called axion kination era to probe such production mechanisms through gravitational waves. So that will be the focus of the talk, and that's what I will begin with in this talk. And then I will give you some intuitive understanding of dark matter and Biogenesis in our framework. Okay, so let me first explain what is axion kination. But to begin with that, I need to talk about what kination actually is in general. So kination is a period of cosmological evolution such that the total energy density of the universe is dominated by a scalar field. And in particular, it's dominated by the kinetic term of a scalar field. So if you look at the equation of state, W, for a scalar field is given by K minus V over K plus V, the kinetic and potential respectively. If it is dominated by kinetic term, then that means the equilibrium state would be 1. And if you look at the energy density evolution as a function of the scale factor R, you will find that for this W equal to 1, the scaling goes as R to the minus 6. So this has been proposed and studied in the literature pretty extensively, especially when people talk about gravitational wave from inflation or production of dark matter. But so far in the literature, what people have usually assumed is that you have some kind of pretty unnatural potential where you have a very large potential energy, and eventually you roll down the hill and get to a very flat era for a very long period of time, where this field energy is only dominated by the kinetic term. So that's what has been assumed in the literature. And what I want to show in this talk is that axion rotation actually gives rise to a much more natural and plausible way to realize kination in general. And this kination era is closely related to the dynamics of the rotational motion that I will discuss. Okay, so now let me define some notations and terminology carefully. So what we're looking at here is the potential energy of a complex field that breaks the Picobreaking symmetry. And this complex field P has two modes, the radial mode and the angular mode. The radial mode, we can assume, for example, in supersymmetry, people call the radial mode the Axion, the scalar partner of the Axion. And the angular mode is the Axion that we're familiar with. It is the radial mode that eventually obtains a VEF of order Fa, and that breaks the Picobreaking symmetry. And Axion is the pseudo non-Gaussian boson of this spontaneous symmetry breaking. And eventually, this axion will obtain a mass from the QCD effects because of the coupling between the axion and the gluons. So in this talk, what differs from the literature is that the literature has considered this kinds of initial condition where the complex field starts with a large field volume and undergoes radial oscillation, or the complex field can start from the origin or already at the minimum of the potential early on in the universe. What I want to propose in this talk is that this does not have to be the case, and there's actually a very well motivated dynamics that have been overlooked in the literature. So what you see on the right-hand side is the same one-body potential, but I would motivate for you why there are actually wiggles along the angular direction when the radial field value is large. And those wiggles will actually give this complex field a kick when it starts to roll towards the origin. So this kick would drive this motion into a spiral motion all the way down to the minimum of the potential. And it is really this rotation that gives rise to everything that we're going to discuss today, including kination, dark matter, and the Baryon Asymmetry. Okay, so now let me explain why we actually think rotation is actually very plausible. So first, I'm assuming two ingredients. One, I start with a very large field volume in the radial direction. And second, I have some angular motion. So let me start with the large field volume. So what it requires is a flat potential in the radial direction. And this is naturally the case in supersymmetry, where the radial mode mass could be, for example, of order the soft mass, as opposed to the decay constant. So this mass of the axion can be much smaller than the decay constant. And that would effectively correspond to a small quartic coupling. But in supersymmetry, we don't need to fine-tune this quartic coupling. It just arises to be small. So once we have the flat potential, how do we know that we can start with the large field volume? The answer is that there are many ways to realize that. One, it can just be an initial condition during inflation. Somebody just put a field there and it's stuck there because of Hubble friction. Another possibility is that there is a Hubble-induced mass. Through the coupling between the axion and the inflaton, you would obtain a mass of order the Hubble scale during inflation. And this Hubble mass could be positive or negative, depending on the model. If it is negative, and if this Hubble-induced mass dominates over the vacuum mass, then this is a tachyon mass that's going to drive the axion to a very large field volume. Eventually, this axion will be stabilized by higher dimension operator. So this is how you can see this field will be driven to a value that is more or less the geometric mean between the Hubble scale and the cutoff scale of the theory. If this dimension is high enough, then this geometric mean is very close to the cutoff scale of the theory. So Hubble-induced mass can easily place the Axion to a very large field volume. And with this large field volume, this wiggles become important in driving the rotational motion, as we will discuss now. So what we need for the angular motion is explicit Picobreaking. And this is actually related to what people call the Axion quality problem. So the idea is that we know there's a conjecture from quantum gravity that gravity does not respect global U1 symmetry. So you always expect some higher dimension operator suppressed by the Planck scale that breaks any U1 global symmetry. In this case, the Parametric symmetry will be broken by a term that looks like this form, p to the n. And this, because there's no absolute value here, so when you add the Hermitian conjugate, this becomes a cosine function. And this cosine function is exactly what you see in the wiggles here on the right-hand side. And this is only important in large field volume because when p gets small compared to the cutoff scale of the theory, then you receive a very large suppression. So p over m, if p is at the minimum of the potential Fa, then this can be sufficiently small that does not contribute to additional mass for the QCD axion. And this is usually what people discuss in terms of the axion quality problem, that you don't want to displace the axion from the minimum of the CP conserving minimum. So for a sufficiently high n, then this would not cause problem in the axion quality problem. However, even if n is large, in our scenario, this could still be significant because what we're saying is that this p actually starts with a field value that's actually very close to the cutoff scale. So even if you raise it to a large power, let's say 8 or 10, the other one factor to the power of 8 or 10 is still sizable in giving an angular kick. And the combination of these two effects would now explain how this rotational motion can arise in the early universe. And more importantly, I should mention that this whole dynamics was motivated by Affleck-Dunn baryogenesis. The one big difference is that here we're talking about the complex field that breaks the Parametric symmetry that includes the QCD axion. In the Affleck-Dunn baryogenesis scenarios, what people consider is the scalar partner of the leptons or quarks that carried baryon number or the lepton number. Other than that, the initiation of the rotation is completely analogous. So this is a very well motivated direction, but somehow it has been overlooked in the literature since Affleck-Dunn baryogenesis mechanism until recently. Okay, so let me just summarize again with a video of my daughter playing this kind of coin donation, if you have ever seen it. So this also explains how the rotation arises. So in this case, my daughter, along with the ramp, will be the explicit Picobreaking terms. That's going to drive the angular motion. And as you can barely see here, the coin is going to rotate in this funnel. And the rotation motion continues, but the radius shrinks. In reality, this is because of friction between the coin and the funnel. But in the cosmological setting, this also happens, except that it is due to Hubble friction. So this rotation motion will start with a large radius, and eventually you get to the minimum of the potential because of the expansion of the universe. And this dynamics would give rise to interesting cosmological eras. Okay, so let's now understand this rotation in a conserved quantity. We know we have a shift symmetry. Soon after the onset of this initiation of the rotation, the conserved quantity can be computed using the shift symmetry by looking at the Noether charge. The Noether charge has this form, P times P dot star minus the Hermitian conjugate. And if you use this expression of the radial mode Axion and angular mode Axion, what you find is that the number density of this conserved quantity is given by the radius square times the angular velocity theta dot. And this is no surprise because this is nothing but the angular momentum in classical physics. This is r squared omega. And this is basically the rotational symmetry in classical mechanics. So we can now say that the rotation has a conserved angular momentum. And we call this conserved charge the Picobreaking asymmetry with the Picobreaking charge number density. And because that's the conserved quantity that this field will carry. And this conserved charge eventually will become, for example, the source of Axion dark matter and also the Baryon asymmetry that we will see. But for now, let me first finish discussing the evolution in the early universe and how this could give rise to gravitational waves signals before I talk about dark matter and Baryon symmetry. Okay, so now let's think about the evolution of this energy density. As we have just argued, the number density of Picobreaking charge is given by s squared theta dot. If I multiply this density by the scale factor cube, this must be the total charge, and it has to be a conserved quantity soon after the onset of the motion. In the conventional scenario, if this field is already at the minimum of the potential, even if you somehow start with a large theta dot, you will see that because s is a constant, then theta dot itself must scale as r to the minus 3, according to conservation laws. Then the energy density of this rotation, which is the kinetic energy, given by theta dot squared fa squared, must scale as r to the minus 6. And this is nothing but kination that we saw in the previous slides. This is the motion, the scaling of kination period. And this is also intuitively understood because when you're at the minimum potential, you have no more potential energy. What you carry is only the kinetic energy. So that also satisfies the intuitive understanding or definition of kination. In our scenario, however, this is not where we start. Where we start is a large field volume. So this S is much larger than FA, and it scales depending on the type of Axion potential. It could be a quartic potential or a quadratic potential. If it is a quartic potential, the field volume square scale as r to the minus 2 versus quadratic potential where s squared scales as r to the minus 3, then you can see according to the same conservation law, theta dot will either scale as r to the minus 1 or it would actually remain a constant. And using this scalings and the rotational kinetic energy, you will find the energy density scale as r to the minus 4, which is the same as radiation, or r to the minus 3 for quadratic potential. And this is the same scaling as matter. What is important about this scaling is that this field, even if it starts with the energy density much smaller than radiation to begin with, this matter scaling will allow the rotational energy to dominate over the radiation over some period of time. And once you have this domination by this matter scaling, when the field radius shrinks to the minimum of the potential, then the energy density scaling changes from r to the minus 3 to r to the minus 6. So in other words, you can first dominate because of the matter scaling, and eventually you transition to kination scaling, where you redshift faster than radiation. And this energy density simply redshifts away. So you can have a period of matter kination domination without transferring this energy into the radiation. So this is in contrast to reheating. For either inflaton or modular reheating, usually when you have matter-dominated era, you have to end it by reheating it. You have reheating the universe. You have to transfer the energy from the matter field to the radiation. In our case, this does not have to be the case because of the fast redshift of kination. So let me summarize this scaling in the next slide after I discuss some of the subtleties. So here, so far, I have been assuming that the whole motion is a perfectly circular motion. You may wonder that in the initiation of the rotation, it's possible that we actually initiate both the angular mode and also the radial mode, because you also have a motion towards the radial direction. the question is, where does that energy go? And in our scenarios, we find that we could thermalize the energy density of the radial mode. And I would discuss in the next slide in more mathematical detail, but the end result is that if you thermalize the radial mode using Picobreaking symmetry conserving interactions, then you can only transform this kind of elliptical rotational motion into a circular motion, as shown in this video. And the main reason is that we're thermalizing this complex field using interactions that conserve Picobreaking charge. So the question is, how can you extract energy out of this motion without violating charge conservation? In other words, how do you extract energy from an elliptical motion without changing its angular momentum? The answer is that you transform the elliptical motion into a circular motion. So that's what happens when the complex field thermalizes with the bath early on in the universe. And this is how the almost perfectly circular motion would result. And this is the assumption that we have had so far. After thermalization, what happens is that this field would experience cosmic expansion. The energy density overall would redshift, and that corresponds to the radius shrinking all the way until you're at the minimum potential, and the complex field will continue to rotate at the minimum of the potential. And that's also where we said the kination scaling will start. Okay, so let me also discuss what happens in details about thermalization. When I say we thermalize the field with the thermal bath, we actually create a little bit of Fermion asymmetry, which means that we're creating more fermions than anti-fermion because of this transfer of charge from the rotation, from the PQ charge into the thermal bath. And the question is, if we transfer this asymmetry, do we actually transfer too much in the sense that we actually completely transfer the conserved charge into the bath? If that happened, then the rotation would not be a rotation anymore. You would just completely remove the rotational energy density and you just reheat the universe instead. As we will show in this slide, that's not the case. Only a tiny fraction of the charge is transferred. All right, so let's work through this simple arguments using free energy in the equilibrium state. So for the Fermion asymmetry, the formula is given by the number density of the fermion minus the number density of the anti-fermion. The expression is mu times t squared. This mu is the chemical potential of the bath. And we know if we're in thermal equilibrium, then the free energy of the system must be minimized. So what we're looking at now is the change of the free energy of the thermal bath once we create some Fermion asymmetry. Then the formula, the standard thermodynamic formula, tells us that it is n psi squared, this asymmetry number density squared, divided by t squared. And the free energy of the rotation is given by negative theta dot times n psi. So now if you want to minimize this total free energy change of the system, it's not hard to see that it's just the balance between this term and that term. And that gives you n psi times t squared. N psi is given by theta dot times t squared over here. And now this is the amount of asymmetry that we create once we thermalize the complex field. But now you can compare this asymmetry we create with the asymmetry that we start with. This is the angular momentum formula that we saw before, s squared theta dot. In our scenario, this s is always much larger than temperature because we start the field value at a place that's close to the cutoff scale of the theory. So this s is very, very large compared to temperature. Then this simple analysis tells you that upon thermalization, what happens is that you have a lot of charge asymmetry, but only a tiny fraction here gets transferred to the chiral asymmetry. So that proves the previous slide that the rotation motion will go from an elliptical one into a circular one without losing most of its charge. And this is what we will assume in the remainder of the talk. What will be important to remember for later part of the talk is this Fermion asymmetry. It's given by this theta dot t squared. This is kind of the standard the standard scenario if you have some asymmetry in the bath, except that in this case, the chemical potential of the fermion is given by theta dot, the angular velocity of the axion. And this would be important when we discuss Baryon asymmetry. But for now, let me continue with the discussion of the evolution and how that affects gravitational wave. And as I mentioned earlier, this is just a summarized figure that we will start with radiation domination.
Raymond,
Yes.
I have a question.
Yeah.
Well, I think it depends on the interaction, just how fast is the thermalization happen. Suppose it's very slow, do you just remain as an elliptical orbit for a long time when you go down to the bottom?
Yeah, so it does depend on the interaction rate. Yeah, when the rate is smaller than Hubble, it remains as elliptical motion close to the minimum of the potential. But yeah, by the time when the rate gets larger than Hubble, then thermalization occurs. And this is actually an important point, because if the elliptical motion is too elliptical, and if it gets to the minimum of the potential before thermalization, then what happens is that you start to probe this kind of non-linearity when the elliptical motion is close or probing the bump in the center. And what can happen is parametric resonance, meaning you can convert this coherent rotation motion into some fluctuations in both the angular direction and then the radial direction. And that could be disaster for our scenario with the rotation. But we do take that into account in the papers. It's not complete disaster for cosmology in the sense that we just lose the coherent motion because of parametric resonance, but what we get is fluctuations. And that by itself could still be a source of axion dark matter. We just cannot use this rotation to produce Baryon asymmetry. Okay, so in this case, so this figure is assuming that thermalization occurs early on, so that it occurs before this rotational energy density shown in blue dominates the total dominates the thermal energy of the universe. In this case, once thermalization occurs, then you remove the energy associated with the radial oscillation. This is the point where you transform the elliptical motion into a circular motion. But as we have shown before, the circular motion would continue to scale as matter. That explains how this blue line can dominate over the red line. And at some point, this radius continues to shrink. It will shrink to the minimum of the potential, and the kination scaling starts to happen here. And the transition of that is that the energy density starts to scale as kination. And eventually, this rotational energy density at the minimum of the potential would simply redshift away compared to the thermal bath. So there is an interesting era of matter to kination domination that's pretty much unique to this kind of axion rotation. And this is what could give rise to unique signatures in primordial gravitational waves. And later on, this rotational motion would continue to lower temperatures, and this could give rise to, for example, Baryon asymmetry and dark matter. Okay, so now one very important point that we should emphasize is that, as I mentioned before, this matter to kination domination exists just by redshift. We don't have to have any further transfer of energy from the rotation to the thermal bath. So there's no entropy production during this matter to kination domination. And in other words, this period can actually occur after BBM and before CMB. Usually you cannot have any matter domination after BBM because you create entropy, and then that would destroy the successful prediction of Big Bang nuclear synthesis. But in this case, we're really just modifying the expansion rate of the universe without creating more radiation. And that allows us to see some unique signatures in gravitational waves that we will see. Okay, so let me define a few variables. So this TRM is the temperature when you transition from radiation R to matter domination M, or TMK transition from matter to kination, and then TKR is from kination to radiation. And these three temperatures uniquely define the amount of radiation, the amount of rotational energy density we have, and the period of matter and kination domination. Because we know the scaling between these two eras, T cube and T to the 6, there's actually a relation between TMK and TKR and TRM, and that's the geometric average. These three temperatures are in turn given by some model parameters, for example, the Saxon mass and the decay constant. The last variable that we need to know to specify these three temperatures is the Picobreaking yield. This is the number density of the Picobreaking charge divided by the entropy density. And this quantity itself depends on the initial condition, meaning how strong is the kick and when does the kick happen in the early universe. That determines the amount of yield. But what we really have in this parameter space is the two parameters, two temperatures, but you can map it onto the model parameters and the amount of yield. And this yield will be eventually connected to dark matter and the Baryon Asymmetry. But for now, when we think about gravitational wave, we can just treat those as independent parameters for now. All right, so that's it about axion kination. So let me now talk about gravitational wave from axion kination. I mean, not from axion kination, but gravitational wave signatures because of axion kination. So there are two types of gravitational wave that we will briefly consider in this talk. One of them is gravitational waves from inflation. The origin of this gravitational wave is the quantum fluctuations of the metric during inflation. And this is a standard way people look for high-scale inflation. The basic idea is that you have fluctuations of the metric. During inflation, they get inflated, so they go out of the horizon. Eventually, when you reheat the universe and evolve, this horizon would cross, or this mode, this wavelength would cross the horizon of the universe again. And this fluctuations of the metric will start to evolve. And that's the origin of gravitational wave. The simple formula is given by this. This is the momentum mode of the fluctuation. And this rho r is the radiation energy density at the time, at the temperature of horizon crossing. And this PT determines the amplitude of the gravitational wave, and it is given by Hubble scale during inflation squared. So it has a very high dependence on the inflationary energy scale. The way we compute this horizon crossing temperature is by definition when the size of the fluctuation, the characteristic length, is comparable to the Hubble horizon. Then we can solve for the temperature of horizon crossing. In the standard radiation dominated era, this Hubble is nothing but rho r at THC. And you can imagine having this k squared, which means that you have h squared, which is given by rho r directly. Then this rho r and that rho r will cancel. So in the standard prediction, you will have a nearly flat spectrum in the gravitational wave signal. So this is the first line here. When the frequency is high enough, so that we're in a region where the horizon crossing occurs during radiation, the spectrum is flat. Then you can also see in our scenario that's different, because in the matter and kination domination, our Hubble scale is larger than that in radiation dominated era because of the extra energy coming from the rotation. With that, you can compute the scaling of the gravitational wave with respect to the frequency of the gravitational wave. And during matter scaling, it goes as 1 over f squared. During kination period, it goes linearly in the frequency. And those f with subscripts simply tell you the frequency at which the horizon crossing occurs. So for example, FRM is horizon crossing occurs at the time of radiation to matter transition. The bottom line of this page is that from the formula, we can see it is directly proportional to the Hubble scale at horizon crossing. And if you have anything other than radiation-dominated era, you have an enhanced Hubble rate. With the enhanced Hubble rate, then you're enhancing the gravitational wave strength. So this matter-to-kination domination that we have gives rise to an enhanced gravitational wave spectrum. And this is, again, in contrary to ordinary reheating, because in reheating, even though you have enhanced Hubble because of the moduli or inflaton domination, this Hubble would eventually transition to radiation by reheating. And once you have reheating, then you create entropy. And this formula does not hold anymore. You have to include the dilution because of the entropy production. And at the end of the day, for their case, the gravitational wave would be suppressed instead of enhanced, again, because of the entropy production. In our case, it's always enhanced. So let me summarize all of this in the figure. So what I'm showing here is first, the black line is the conventional prediction. If you assume the scale of inflation to be around the current cutoff scale or the current experimental bound, 1.6 times 10 to the 16 GeV. In this case, it's quite hard to probe it. If we're lucky, we may be able to see it in BBO or dicycle. But if this scale is just slightly smaller, then this curve will drop very quickly. Then we have no signal possible. In our scenario, we have a matter-to-kination domination. As we argued before, it only increases the gravitational wave strength. So let's take this curve, for example. The way we read the upper axis is that on the left-hand side, there is a crossing point, and that crossing point corresponds to TKR. So for example, for this curve, TKR is about 10 megaelectron volts. And here, this is TRM corresponding to 10 to the 7 GeV. So if we have some cosmology that has this TRM and TKR, then this flat spectrum becomes enhanced and features this triangular peak. So this is the unique signature for axion rotation or axion condition, to be exact. That will give you an enhanced gravitational wave spectrum. And not only that, we predict the slope here and there that we have described in the previous slide. And we also predict a peak in the spectrum. So by measuring the peak strength and the slope, we will be able to confirm whether axion kination is at play. And also that will help us determine TKR and TRM. And I would draw your attention to this particular curve. This curve is actually, especially the left edge. The right edge is dependent on the initial condition, but the left edge of the plot is axion dark matter coming from the rotation. It's a prediction, not a free parameter. So axion dark matter coming from rotation predicts that the QCD axion must have a TKR of order 10 to the 6 GeV. So by seeing this kind of signal in BBO, dicycle, or if we're lucky in CE, then we may be able to verify this entire scenario. All right, so the next example of gravitational wave I want to discuss briefly is coming from the cosmological or cosmic defects. So for example, when you have the local U1 symmetry, so I'm not talking about the particular symmetry anymore. I'm talking about some, for example, dark U1 that undergoes phase transition in the early universe. In that case, then you can form so-called cosmic strings. And the cosmic string is just the topological defects where the field at the minimum of the potential would wind the potential in one circle, and that corresponds to the line here. But that means at the center of the region, the spatial region here, the field is corresponding to where it started with the origin. So there is some topological defect here. That is the cosmic string. And this cosmic string would vibrate and close and emit energy in the form of gravitational wave. So this is how the cosmic strings will eventually decay away into gravitational wave. The discussion of the scaling is quite complicated. compared to inflationary gravitational waves. The reason is that we now have to talk about two time scales. One is the formation of the loop coming from the cosmic string. Those strings would form loops and then shrink. The formation would affect the gravitational wave spectrum, but also the decay of the loop would further affect the gravitational wave spectrum. So this table summarizes the scaling in different combination of possibilities. What is really important again here is that the gravitational wave strength is still enhanced because of the matter to kination scaling. So it may be easier if I just summarize this scaling in a figure. And this mu, as I mentioned here, that's the string tension. For different choices of string tension shown in different colors, we have different gravitational wave spectrum. The solid line here continuing in the dashed line is the conventional scenario. That is if you have the formation of the loop and decay of the loop both in radiation dominated era, then the spectrum is flat. Otherwise, you get enhancement because of the formation during matter dominated era and formation during kination dominated era. So for different colors, they again correspond to different string tensions, and different bumps of the same color corresponds to different choices of the temperatures, TKR and TRM. Then we would be able to use, for example, this unique triangular peak to distinguish our prediction of the gravitational wave spectrum compared to the conventional one. And also, again, if you measure the peak and slope, then you'll be able to determine the temperatures. And those temperatures can in turn tell us the parameters of the theory. Okay, so this is more or less what I want to talk about for of the kination matter domination before BBN. And this plot is going back to the statement that this matter to kination era does not end by reheating, so no entropy production is needed. So this can happen after BBN and before CMB. And this is what this plot is showing. For this choice of string tension, I can take TKR as small as 150 EV so that I don't spoil CMB. And then TRM can be as large as 6 keV so that I don't spoil BBN. Then with these choices, then I will be able to, for example, explain the tentative signal in nanograph, PPTA, and EPTA, where they observe axis of the gravitational wave events around nanohertz frequency and the strength of order 10 to the minus 9. And if we're able to measure experimentally the actual strength more accurately, we will be able to determine the string tension. And if you can measure the spectral tilt very precisely, then we will be able to distinguish our scenario from the conventional prediction of radiation domination. And again, this is extremely unique to axion rotation because this has to happen after BBN and before CMB. And to my knowledge, there's no other ways to realize this enhanced Hubble scale after BBN and before CMB other than this axion rotation. Okay, so that's the discussion I want to have for gravitational wave. So next, let me go back to how we could actually use this axion rotation to produce Baryon asymmetry. We actually have most
Sorry,
likely.
before going on, can I ask a question?
Yeah, go ahead.
Not a question, actually, I want to understand. So basically, you want signature, like the energy density goes like R to the minus 3 power, but still you have some movement, some kind of velocity. Then you can have some enhanced signal. Is this summarize what you are doing?
When you say
On the one, I'm trying to understand the whole idea. On the one hand, you want this is the kination like a decrease like a matter domination, but on the other hand, you need the kination have some kinetic energy. Then that's why the signal can be enhanced.
So yeah, let me summarize it this way. So the reason, pretty much the only reason that the signal can be enhanced is because of a larger Hubble scale. in the relevant eras. By relevant, I mean for the string, cosmic strings is the formation and decay eras. The Hubble scale is larger than radiation domination. And then we do it through matter to kination domination. And matter and kination domination eras are kind of automatic if you have this axial rotation for long enough. And this matter and kination scalings are separated. So I'm not trying to get matter and kination, let me see, like at the same time or anything like that. So the matter scaling just starts already if you're rotating around the body of the one body potential, like right here on my left. So this rotation phase is the matter scaling. When you get to the minimum potential, this rotational phase is the kination scaling. And this can be seen just from conservation of charge. But you can, we also solve the equation motion and verify the scaling. Does that answer the question?
Okay, we can go on.
Okay, all right. Yeah, I'm happy to answer more questions if that's not clear. Okay, so now let me talk about baryogenesis, how this could give rise to the Baryon symmetry of the universe. And we actually have seen most of the ingredients in the earlier part of the talk. So this is what we call axiogenesis, is the combination of using the QCD axion to do the job of baryogenesis, specifically using axion rotation. And what is very exciting in this scenario is that we will be able to explain multiple unsolved puzzles at once in one model. For sure, we have the strong CB problem that the QCD axion was proposed to solve, and we can use the axion as dark matter. And what is different in this case is that the dark matter abundance of axion does not come from the conventional misalignment mechanism, but it comes from the kinetic energy of this axion rotation. The third puzzle is the Baryon asymmetry that also comes from this rotation. Okay, so the basic idea is this picture that you have seen before when I talk about thermal equilibrium. We argued that we create a small chiral asymmetry in the bath that's of the form theta dot times t squared. This is just coming from the minimization of the free energy. In the case of QCD axion, this process, this transfer will occur through the standard model strong spheroid. So this is more or less guaranteed by construction that you have the axion gluon coupling. So this Picobreaking charge would now transfer to quark chiral asymmetry. You have more quarks than antiquarks. But at this stage, you still have a zero baryon asymmetry. But what happens is that this electroweak spheroid processes of the standard model will further reprocess this quark chiral asymmetry into the baryon asymmetry. And eventually this charge goes from the PQ rotation into the non-zero baryon asymmetry. And the expression is given by this. This is some theta dot times t squared coming from here. And this dimensionless CB coefficient tells you how efficient this transfer is. This S is the entropy density. So this quantity scales with the temperature. The question is when we evaluate this expression to get the final baryon symmetry, the answer is the electroweak phase transition temperature. Because at that point, then the electroweak spheroid processes go out of equilibrium, then the transfer stops. The number density of the baryon gets frozen. So now we can evaluate this temperature at T electroweak, and then we normalize theta dot to be a scale invariant quantity or redshift invariant quantity YPQ, so that I can relate this YPQ with the earlier three temperatures that we were looking at. Now, if I just put in numbers, this Baryon symmetry tells you that if you want to reproduce the observed amount of order 10 to the minus 10 using the prediction of the standard model on the electroweak phase transition temperature, you need this FA to be of order 10 to the 8 GeV if the yield of the Picobreaking charge is 500. So there's some relation between FA and YPQ that allows you to explain the Baryon symmetry. And that already gives you some requirement on the three temperatures that we discussed, even though it does not make a prediction yet. Okay, so this is the basic idea for axiogenesis. But let me also mention that that's not the only way you can transfer the Picobreaking charge. It depends on whether your model has additional baryon number or lepton number violation. In the case of the neutrino mass coming from the Majorana mass term, this dimension 5 operator, this 1-bar operator will violate the lepton number. In that case, then your system has a violation of lepton number, and you can go through this kind of charge transfer. So I won't go into all of the details, but the idea is that you transfer this PQ charge from the strong spheron, and everything in the middle here is just the standard model Yukawa couplings and electroweak spheron processes. You will start to create the Higgs number, lepton current symmetry, which eventually gets converted into the lepton symmetry. And this lepton symmetry, just like in leptogenesis, can get transferred to the Baryon symmetry through the standard model electroweak spheron. What is qualitatively different in this scenario compared to the minimal axiogenesis scenario is that you can produce this lepton number at a very high temperature, and this B minus L does not get washed out by the standard model electroweak spheron. So these two boxes here can happen at different times. You don't need to have them, for example, in equilibrium simultaneously. You can produce a bunch of lepton number at a very high temperature, and then just store it as B minus L, and it remains as the conserved quantity even past the electroweak phase transition. So then the evaluation of the Baryon symmetry would not depend on the electroweak phase transition temperature anymore. For the interest of time, I would just tell you the essence of the calculation. So the yield of this B minus L asymmetry is given by the same expression, theta dot times t squared, and now you have a different coefficient for the efficiency of transfer, but this coefficient is always of order 0.1. And now we have additional suppression here, because this rate, this lepton number violating rate, may not be in thermal equilibrium. If it is not in thermal equilibrium, you still produce lepton symmetry, but you just do not saturate the thermal equilibrium volume. So you can think of this as a freezing production of the lepton asymmetry. And this is the freezing suppression in this case. And looking at this expression, looking at this expression, then it turns out that it's quite complicated to discuss in which era this production is dominant, because you have to talk about, for example, radiation, matter, kination, and yeah, so the evaluation of this expression gets dependent on the cosmological evolution. And that's what we discuss in very detail in this leptoaxiogenesis paper. And the paper is extremely long, it's like 70+ pages, but that's not because of the mechanism being complicated, it's just because there are a lot of different cases in the cosmological evolution. And the end, yes.
Do you need kination domination in those scenario or?
Yeah, good question. So in both axiogenesis and leptoaxiogenesis, kination domination is not required, but it just happens that in some parameter space, some regions, this automatically happens. In some other regions, this just does not happen. Yeah. Okay. Yeah. So at the end of the day, we found a viable parameter space with, for example, supersymmetry scale of order 10 TeV, and everything's consistent. All right. So one more quick mention of the possibility of a different lepton or baryon number violation. In supersymmetry, there is the possibility of the all parity violation. All parity violation violates lepton number or the baryon number, or both of them. In all of these cases, then it is possible that the carrier symmetry gets transferred to B minus L at different temperatures compared to, for example, electroweak phase transition or the lepton number violation from the neutrino mass term. So the evaluation gets different as well. So we also make predictions in this paper. And the end result is, again, that we would prefer the QCD axion to be the heavier side, meaning around milli-electron volts to 0.1 electron volts. So those are these different variations they can have in axiogenesis to explain the Baryon symmetry. All right, the last thing that I want to touch on is dark matter. How does this rotation eventually give rise to dark matter abundance? And after this, I would put everything together to show you the parameter space where we produce dark matter, Baryon symmetry and have gravitational wave signals. So let me first say the conventional misalignment mechanism is such that there's a misalignment from the minimum of the potential, so that this axion field has non-zero potential energy. And when Hubble drops below the mass of the axion, the Hubble friction becomes negligible and the axion starts to oscillate towards the minimum potential. In our case, because of the rotation is eventually the kinetic energy of the axion when you're at the minimum potential, then that means you come with a very large kinetic energy, so large that you actually overcome all of the barriers in the cosine potential. So initially you're in a rotating phase where you're just riding on the cosine wave. And eventually when cosmic expansion is long enough that you redshift the kinetic energy sufficiently, that you lose the kinetic energy to climb over the last barrier. And that's when you start to oscillate towards the minimum potential. And that's illustrated in this animation. So this part is the conventional misalignment, where you just oscillate around the minimum very quickly. And at that point, the rotation can still happen in our scenario until the kinetic energy gets redshifted so that you cannot overcome anymore. And then get trapped in one of the minima, and the oscillation starts around the minimum. So the basic way to think about why this gets enhancement to the dark matter abundance is that you start with a lot more energy, but only stored in the kinetic term, not in the potential term. So that's why you have more energy in the kinetic misalignment than conventional misalignment. Or another way to say it is that when the conventional scenario has the oscillation, we are still in a rotating phase. So effectively, we're delaying the onset of oscillation, and that delays the redshift. Now, if I put the numbers in for the final expression, so the dark matter abundance of the axion is given by some order 1 coefficient times the axion mass times the yield of the Picobreaking charge. If I put in this number and see what I need to explain the dark matter abundance, what I get is that for the axion mass of milli-electron volts, I need a yield of around 440. So this is somewhat close to the 500 number that we saw before when we had that benchmark point for the Biogenesis. But now let's put everything together to see some problem space. So if I require both dark matter and the Baryon asymmetry, for ELP, that's where we are. For QCD axion can live somewhere towards the larger axion mass regime. So that's the prediction. On the right-hand side, I'm showing the prediction on the temperatures now. The y-axis is the decay constant. The x-axis is the axion mass. The blue lines are the predictions if we require axiogenesis or just ELP-genesis, if that's not the QCD axion. The lines are here. That's the prediction of TKR equal to 1 GeV, and this is TKR equal to 1 TeV if I require baryogenesis. And instead, if I require dark matter abundance coming from this kinetic misalignment mechanism, then the purple lines show the prediction of TKR of order GeV or of order TeV. And then the conventional QCD axion relation between FA and MA is right here. That's just a conventional one. And now you can see this line, this prediction of dark matter abundance is actually parallel to the conventional prediction of the QCD axion, which means that the line that's sitting on top of this QCD axion line is around 10 to the 6 GeV. And that is the prediction that if the dark matter abundance of the QCD axion comes from kinetic misalignment, then TKR must be around 10 to the 6 GeV. And that corresponds to the specific curve that we were looking at, for example, this one. So that's the origin of where this TKR 10 to the 6 GeV comes from. So that would be the prediction. And on the right-hand side, let me just show you one scenario where we put everything together and see the region that can be probed and so on. The vertical axis is the decay constant, and here's the axion mass. The horizontal axis is the mass of the axion, meaning the radial mode in supersymmetry. And this hedge region is where we're able to explain the Baryon asymmetry using lepto axiogenesis. TKR is predicted to be around 10 to the 6 GeV from the QCD Axion dark matter requirement of kinetic misalignment. And what is shown here is that you see two thick lines, BBO and dicycle. Both these thick lines, this enhanced spectrum gets into the detectable region of dicycle and BBO. And on top of that, this shaded region of the BBO and dicycle corresponds to the scenario where the peak of the triangle spectrum even falls into the BBO and dicycle region. So not only do we get an enhanced signal, but we actually resolve the triangular peak. And I would say that would be the smoking gun of this whole scenario. So in this region, this is the highly motivated region where we explain dark matter, Baryon symmetry, and have unique signatures in gravitational wave. Okay, so this is just a flash of similar results of where we can have Alpgenesis. And this is using different gravitational waves experiments, LISA, ET, CE, dicycle, BBO, above the solid thick lines. We can probe those white regions. Those are the viable parameter space with gravitational wave. And the shaded region of each experiment shows the region where you can resolve the triangular peak. So the cosmic strings are good at probing TKR and TMK at high temperatures. The inflation are good at high temperatures, and the cosmic strings are good at probing low temperatures. So the bottom line of these two figures is that they're in the open parameter space, some of them can be probed by gravitational wave signatures if we require Alpgenesis. And sometimes we also require dark matter abundance in this parameter space. Okay, do I still have like 2 more minutes?
Yeah, go ahead.
Okay, all right. So for the last 2 minutes, I just want to discuss something quite interesting. In the discussion of the evolution so far, I've been assuming that the transition from the matter scaling to the kination scaling is a sudden approximation, that the equilibrium state suddenly jumps from 0 to 1. In the reality, it is not the case. It depends on the exact potential in the radial mode. If the potential has a certain form, then we actually can know the evolution of the equilibrium state precisely. For example, in supersymmetry, there are 2 motivated scenarios. One is that the radial mode has a nearly quadratic potential, but it has a logarithmic correction coming from the rounding of the soft parameters. So this quantum correction gives rise to the deviation of the potential from quadratic, and this log potential would predict this equilibrium state going like this. So in the large temperature limit, it approaches matter. In the low temperature, it approaches kination. Similarly, you can have a different 2-field model scenario in supersymmetry, where you have this superpotential, and this X is the auxiliary field that fix the moduli P and P bar, the 2 complex fields, into the moduli space. And eventually this model predicts evolution in the blue band here. So this matter to kination scaling could depend on the potential that you have. And because of this evolution of the equilibrium state, the sharp triangle peak that I showed earlier is not the exact result. The exact result would be this line here, that's from the log potential, or from this blue band here, that's from the log potential. Similarly here. So what this really means is that if you're able to observe this triangular peak in the gravitational wave spectrum, if you measure the slope here and there, and then carefully measure the peak of the triangular spectrum, then you can even distinguish how the particular mechanism was broken by some physics that is a very high energy scale. For example, 10 to the 6 GeV. That's for example, the mass scale of the Axion. And just with gravitational wave alone, you can actually know the model itself, whether it's coming from a log potential or a 2-field model. All right, so just 1 more minute to say that we mentioned that this rotating field can dominate the energy density of the universe. And it is possible that this rotating field creates entropy, even though I said we don't have to. But if it does create entropy, then we also create cosmic perturbations. If we create cosmic perturbations, then there's non-zero observable non-Gaussianity that we can observe in the CMB. So that would be another additional signal that we may have in this paradigm. Okay, so I hope I convinced you that this rotational dynamics is well motivated. It can solve multiple mysteries of the universe, and it even predicts interesting signals in gravitational wave spectrum. And there are other potential signatures that I didn't have time to go into in this talk. So this opens up new model building opportunities. Thanks a lot.
Okay, any other questions?
For this Genesis, you just don't assume they are QCD axions, or
Did you say I do assume or I don't assume?
you don't assume it's a QCD axion, you just assume it's some
Yeah, we start. Yeah, we studied both cases. So in some cases, we do assume QCD axion, for example, this probability space. But in some other cases, we relax the assumption and just assume that's some ELP doing Biogenesis. So we consider both scenarios.
But for this case, that this ELP potential also have this whatever this bump from like QCD, right? That's I mean, this explicit breaking from the anomaly, or
Yeah. Oh, so are you talking about the ones at the minimum or at the large?
yeah, the minimum.
Oh, in the minimum, then yeah. So that could just come from some explicit UN symmetry breaking. It could come from some anomaly of some additional SU3, the dark SU3, for example. So yeah, in that case, we're not really sensitive to the origin of this ELP mass. It can come from anything, but it just cannot come from the QCD dynamics, because otherwise it would have been the QCD axion. Yeah, so in some cases, you don't even need to have a mass for the ELP if it is not dark matter. If that's not dark matter, then you could have this matter kination scaling forever. That it just scales the kination forever because it keeps going in a rotating phase. It never feels the mass if there is no mass at all. So that's also another possibility. Yeah, so for example, in the plots here, if I only require ELP genesis, I don't require dark matter abundance. So in principle, the Axion mass, the ELP mass can be 0. We could still have this successful Biogenesis and with some signals from gravitational wave observations.
Let's thank Raymond again.
Thank you. Thanks a lot.